All right, so we just got done in the last modules talking about density along a given direction. Now let's look at density in a plane, therefore planar density. So just like with linear density, the planar density represents the packing, the atomic packing on a given plane defined by us. So we call that planar density, or sometimes shortened PD, and this is the fraction of the occupied area on a given crystallographic plane. So how much area do atoms cover on a given crystallographic plane? And so for the purposes of these calculations, we're going to say that the atom has to be centered on the plane. So basically, the center of the atom, like you can see here, has to go through the plane. So that makes it a little easier to calculate than trying to have to worry about quarters of planes and things like that. So only if the atom is centered on the plane within the unit cell is it calculated. And then we also look at the unit cell area of that plane. So again, like I mentioned in the previous videos for linear density, this definition is going to be different than the one in the book. So make sure you use the ones that we define here in the text. They, again, use this number density, which I don't think is as representative as what we are talking about. So let's go ahead and look at the procedure and the definition of planar density. So again, this is the one that's different than in the text. You'll need to use this one, not the one in the textbook. So always have that caveat. If you want to look in the book for additional help here, keep in mind the differences between this equation and the one that they use. But the procedure is going to be very similar to linear density. We're going to start out by sketching the feature, in this case the plane. That way we know what we're looking at. Then we're going to determine the area of the plane within the unit cell, and we do that in terms of the lattice parameter, so A if we're talking about just a cube. Then we're going to determine the number of atoms centered on the plane. So here we might have to deal with fractions. But again, that caveat of atoms centered on the plane. And then, as always, we have to have that relationship between A and R. And so we do that if we don't already have that known. And then that allows us to simplify and solve the expression of planar density to come up with a fraction or a decimal. All right, so let's look at it and let's do it. Let's start out with simple cubic and let's do the 1, 0, 0 plane. So the first thing we need to do is sketch. And so let's do that. So here, the 1, 0, 0, if you take the reciprocals of that, that's 1, infinity, infinity. And so that means that it's going to intersect the x-axis at 1, which is right here. And then it's going to be infinite, infinite on the other, so it runs parallel. So if you basically make a point on the x-axis and then draw a plane parallel, you get this type here. And so for ease, we're showing the one here in the front. All right, so I've drawn the plane here within the unit cell, and then I can also redraw it just in planar view so you can kind of get the bigger idea of what's happening, where the red square is the 1, 0, 0 plane, and then the atoms here are the blue, and you can see the fraction that's within the unit cell based on the shading. And so we know that that length is A, we know this radius is R, right? So we got a good start on this problem. So now we want to determine the area of the plane in terms of the lattice parameter, right? So our plane is this within the unit cell. We know that the edge length is A, and since it's a cube, they're A in all directions. So the area of a square is going to be A times A, or A squared. So we know that since this is one of the cube faces and it's square, it's going to be the side length A, or lattice parameter A squared. All right, so now let's go ahead and move on to the next step to determine the number of atoms centered. right? So if you're counting them, you see here, 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 and here, right? But the thing to note here is that so we are looking within the unit cell, right? That's the caveat of all of these expressions. And so even though this is one atom, total one atom here, 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 and here, only a fourth is actually within the unit cell. So I'm not going to count this as one, and this is one, and this and one, and this and one. I'm going to only count this as a fourth, right? Because this is a right angle, and if we look at the circle here, we're only taking 1/4 of it. You can do it by angle or however you want to do it. But this is 1/4 of that circle, and so all of these are 1/4 if we look at it in the planar mode. And so instead of counting 4, we get 4 times 1/4, right? So we have 4 1/4 portions of an atom within the unit cell. Because what we're going to do is, since we are looking at the area within the unit cell, we need to count the atoms within the cell. And so that's how we get to 1. So it's only 1 in this case. And so that gives us the top. And so that's the count of the atoms, and then we're multiplying by the area of an atom, which is going to be pi r squared. So that's basically how we get the area of atoms within the unit cell over the area of the plane within the unit cell. So basically at this point, all we have left is to calculate the relationship between A and R. We did this in the linear density calculations. We saw that it was the edge length, and so we saw that A equals 2R. So if you want help on finding this, go back to the linear density videos for simple cubic, and you'll see that example. All right, so we've got all the parts now. We have one atom multiplied by its area, pi r squared, and then the bottom is A squared, and then we use the conversion of A to R to plug in 2R there. And what we're going to find is that we're going to get 4R squared on the bottom, R squared on the top. Those R squareds cancel out. So we're going to have pi over 4. That is an acceptable answer. I tend to prefer the decimals because I like to see that this kind of in terms of a fraction or a percentage. So what this tells us is that this arrangement of atoms on this plane covers roughly 73.5% of that plane, and then the rest of it is empty space. So you can kind of see the empty space here. That's the other, 24%. 26% roughly. So that's what this number is telling us in terms of packing. All right, so we'll go ahead, and the next module we'll go through another worked example.